Hi everyone. So we're going to solve a few more slightly more complicated recurrence relations using generating functions. The basic technique will be the same. There's going to be a setup, a rewrite, some algebra, and then some calculus. That's in common to all of these problems that we are going to do. So first is the setup. I'm going to do a recurrence. This is a sequence defined recursively by a of n equals a of n minus 1 plus 6 a of n minus 2, where n is greater than or equal to 2. And there are going to be some initial conditions here. I need two initial conditions because this doesn't kick in until n is 2. So I'm going to say a of 0 is 0 and a of 1 is 1. So this is actually the sequence that I'm trying to find a closed form expression for. And just like last time, I'm going to introduce a function, g of x, which is the sum from n equals 0 to infinity a of n x to the n. And this function will give me some structure that I can use to determine how this sequence works. I would say that this is the sequence, or the setup portion of my problem. Now, let's move on. So I can take my initial equation, multiply everything involved by x to the n, and then, because this is valid for all n greater than or equal to 2, it's also going to be valid if I start at 2 and just keep adding up. So if I throw summation as n goes from 2 to infinity on here, this is still a valid relationship. Now, I'm going to rewrite this, so notice something with me here. This blue dot term is almost the same as g of x. This is g of x minus the first two terms. So let me leave that here for now. On the next expression right here, I can factor out an x because I know that n is at least 2, so I know there's an x in all of these. This is x times the sum from n equals 2 to infinity, a n minus 1 x to the n minus 1. And then on the next term there's a 6 and there's an x in common to all of these. Actually there's an x squared because n is at least 2. So 6x squared times the sum from n equals 2 to infinity, a n minus 2 x to the n minus 2. Okay, so I have factored this out now, and this is almost done with the rewriting portion of things. So this a of 1 was equal to 1 and a of 0 was equal to 0. So I can rewrite this as g of x minus x. On this one I have to think about what's actually happening with my index shift. So I'm starting at 2, but everything is getting shifted down by 1. So I could shift everything down by 1 and just start at 1. And then on this next term, everything starts at 2, but then the coefficients and the terms are getting shifted down by 2. So I could just start at 0 and not do the shift. Okay, now let's do a little more. This is exactly g of x. And this is almost g of x. This is g of x minus the first term, so this is g of x minus a of 0, which is 0. So now what I have is I have this relationship g of x minus x equals x times g of x plus 6x squared g of x. Okay, so now I can use this algebraically to solve for g of x. So let me get all of the g of x terms on one side and all of the not g of x terms on the other. And now that I've done that, I can factor out g of x. And this should be x, not g of x, sorry. And then I could divide by 1 minus x minus 6x squared. And I've done it. Congratulations, everyone. We have found the generating function of our sequence. However, there's something unsatisfying about saying we found the generating function, because the reason we wanted the generating function was so we could know what the terms were. And this doesn't tell us what the terms of the sequence are. We're going to need to do a little bit of calculus to do that. And so actually I'll start that in the next video.